Semantic caching is becoming the backbone of enterprise AI, but it's built on a fundamental heuristic, vector similarity thresholds. The idea is simple. If two user prompts score above a certain cosine similarity, you assume they ask the same question and reuse the cached answer. But in a governed domain, that's dangerously incomplete. Similarity thresholds have no notion of authorization, no versioning, and crucially, no rigorous definition of when two demands are actually the same. You cannot certify reuse on a distance metric. What we need is a mathematically characterized quotient of resolved conversational demands. Instead of guessing sameness, we define it. The core insight is that reuse should operate on a partition of utterances that is invariant under a strict refinement chain. Reading identity, resolution identity, and reuse identity. When these conditions are met, the pipeline's outputs are provably invariant, and the reuse quotient becomes the exact kernel of the resolution map into the governed answer partition. This isn't a relabeling trick. It's a structural guarantee that measures realized demand, not just corpus structure. Let's walk through how this actually works. We start with an utterance. In a governed system, we don't get clean questions. We get ambiguous strings like "tell me about Paris," "can you do something about this fee?" or "what about last month?" These are ambiguous across at least three axes: the underlying question, domain competence, and whether enough material facts are disclosed to isolate a single answer. Retrieval pipelines usually dissolve this by ranking documents against the raw text. But that leaves the system with no representation of the question it's actually answering. Our pipeline fixes this with three strict gates. Gate 1 checks canonicity. Is this a genuine inquiry from an ignorant speaker to a competent addressee? If not, it roots out. Gate 2 checks admissibility. We filter the candidate readings to only those whose denotations fall within the admissible closure of the governing corpus. Gate 3 checks specificity. We enforce a threshold to ensure the resolved proposition is precise enough to warrant a certified answer. If the survivor set is empty, or if the surviving denotations span multiple cells in the answer partition, the pipeline doesn't guess. It routes to governed abstention and triggers elicitation. Now here's where the formal machinery kicks in. We define two normal forms. First, the cell normal form. For any cell in the partition, we take the set of all closed formulas that denote exactly that cell, and we pick the lexicographically shortest one. This becomes the reuse key. Second, the proposition normal form. For any admissible proposition, we do the same thing, but we require exact denotation, not containment. Why exactness? Because if we allowed containment, the formula for contradiction would denote the empty set, which is a subset of every cell. That would collapse the entire normal form into a single trivial output. Exactness preserves injectivity. If two normal forms are identical, their denotations are identical. With these normal forms in place, we define the three equivalence relations. Reading identity means two utterances survive with theory-equivalent candidate readings. Resolution identity means their aggregated resolved propositions are identical. Reuse identity means they resolve into the same cell of the governed partition. These form a strict refinement chain under realized non-degeneracy conditions. Crucially, reuse identity licenses the governed query key and its certified answer space. But it does not automatically license a particular stored answer. For that, you need resolution identity or an independent applicability certificate. In short, reuse identity reuses the question. Resolution identity reuses the answer. The central object here is the realized governed reuse space. It's the quotient of resolved utterances, modulo reuse identity. The resolution map factors through this quotient, and the induced map is injective. This means the quotient isn't just a cosmetic partition of the corpus. It's a structural measurement of realized demand. If a cell has no realized utterances, it's a governed question nobody has asked. The quotient captures what's actually being queried, not just what's theoretically possible. You might ask, is this even computable? Yes, but conditionally. We quarantine non-computability entirely in the proposal layer, which we assume is total and computable. Everything corpus side is unconditionally decidable. We represent propositions, cells, and specificity thresholds as bit vectors over a finite materialized world set. Gate checks become lookups and inclusion tests. Cell assignment reduces to containment checks, which are linear in the number of worlds. For ground horn programs, closure computation runs in linear time via indexed forward chaining. The data complexity is polynomial, and the combined complexity is exponential, but in practice, corpus compilation is offline. Query time operations are governed by the polynomial regimes. The normal forms are computed once per cell and cached. The runtime cost is dominated by cell assignment and one closure application. Let's talk about safety. In formal verification, we have to be precise about what a system actually guarantees. We define three orthogonal properties. Policy admissibility. Every omitted proposition is in the admissible closure, clears the specificity threshold, stays within its cell, and carries a derivation witness bound to the fiber. Factual grounding. Every premise rests on verified live case facts. Intent fidelity. The answer resolves what the speaker actually intended. This pipeline proves policy admissibility for arbitrary proposers, including adversarial ones. The closure checks licensure, not evidence. grounding and fidelity are enforced by separate evidence and intent layers. The pipeline explicitly does not claim them, and that honesty is a feature. It localizes the fidelity risk to the auditable reading set and surfaces the canonical question for user confirmation before emission. When the pipeline hits ambiguity, it doesn't fail silently. It triggers elicitation over cell-decided predicates. We assume an elicitation vocabulary, where each predicate has a constant truth value on every partition cell. We define an observational signature for each cell based on these predicates. The elicitation policy asks a separating predicate, eliminates cells that contradict the reply, and repeats. Under target consistency, this procedure is guaranteed to terminate in at most the number of cells minus one informative replies. It's sound, the intended cell is never eliminated. If the vocabulary runs out, it reports a containment in an ambient observational equivalence class. If the evidence is inconsistent, it reports no compatible cell and routes to human escalation. It never certifies a negative without complete, truthful evidence. This framework replaces heuristic similarity with a provable quotient space. It separates the untrusted proposal layer from the deterministic verification layer. It guarantees that certified reuse is keyed on a mathematically rigorous identity, not a distance metric. And it does so with polynomial query time complexity over materialized bit vectors, while explicitly bounding its own safety guarantees. The future of governed AI isn't about better embeddings. It's about formalizing the boundary between what a system can say, what it has been asked, and what it can safely reuse. This quotient architecture provides that boundary. It turns semantic caching from a statistical guess into a certified, auditable, and computationally tractable foundation for enterprise AI. If you're building systems where reuse, compliance, and deterministic resolution matter, the math is no longer optional. It's the only way to guarantee that when you cache an answer, you're actually answering the same governed question.